want to continue our lesson, chapter 30, total internal reflection. Okay, today we want to talk about refractive index and critical angle. Now, refractive index, we talked about it before. You remember the symbol of it is n. We said we have two formulas to find the refractive index. The first one is the speed of light in air over speed of light in any medium, okay? And the second formula is the n equals sine of angle between ray in air and normal, sine of angle between the ray in glass and normal. Now we want to see the refractive index when we have a critical angle. What will happen? Look, let's read this example to see. If the critical angle of glass is 42, so critical angle is 42. Calculate its refractive index. They want the refractive index n. Okay, hello, we know critical angle, what does it mean? It is the angle of incidence. Angle of incidence is the critical angle. So here, angle of incidence is what? Our critical angle is uh, critical angle is 42, okay? And here, what do we have? The refracted angle. Refracted angle here is 90 degrees, the angle between the normal and the refracted ray. So, how to find it? N equals sine of angle between ray in air and normal, sine of angle between ray in glass and normal. What is the angle between ray in air and normal? Here is the ray in air and normal. It's 90 degrees, so sine 90 over sine what? Angle between ray in glass and normal. Here is the angle between glass and normal. It is 42. Sine 90, we know it is 1. 1 over sine 42. The answer is 1.5. So the refractive index for glass is 1.5. Okay? Let's see another example. If the critical angle of diamond is 24, C is 24. Calculate its refractive index, the same thing. We use the formula n equals sine of the refracted ray, that is 90, over sine c. Girls, I know you are C teacher. This angle is not given in the question. How did you know it? Because you have to know. When they say critical angle, you have to know by yourself that the refracted ray, the angle between it and the normal is 90 degrees. We said that before. This is the meaning of critical angle, okay? A critical angle, it means it is the angle of incidence. So the angle of refraction, what is it? It is 90, always, okay? So the answer here at the end is 2.5, okay? Good. I hope that critical angle and refractive index now are clear. Let's continue. We have sometimes what happens when we look at the mirror, we see multiple images in a thick glass mirror. Okay, that's what we see. Here's the object. We see the image is what? Multiple images, blurred, not clear. Why? Let's read and see. An ordinary mirror, silvered at the back, forms several images of one object. Hello, we know this is a mirror. Here is the surface of the mirror, the front surface. This is the back of the mirror. It's made of what? We said mirror, it's made of a glass, and the back of it is silver. Silver because it reflects light, okay? So we talked now. When light will enter the glass, what will happen to it? Before it reflects from this silver surface, what will happen? Especially mirrors, they have thick glass, not thin glass. It will refract and some light will reflect. We said that. Okay? Refract and reflect. So because of multiple reflections inside the glass, these blur the main image I. This is the main image I, which is formed by one reflection at the silvering, especially if the glass is thick. And we have this case when the glass of mirror is thick. So we have refraction and reflection at the same time. Okay, the problem is absent in front silvered mirrors, but such mirrors are easily damaged. If we want to fix this problem, what we can do, we can silver the mirror from the front, not from the back. But what's the problem with this thing? That these mirrors are easily damaged. Okay, these mirrors are easily damaged. That's why most of the mirrors they are silvered from the back, not from the front. And we have glass first, then the back of it silver. Okay, let's explain again what happens exactly to know what does it mean. The front surface of a thick mirror both reflects and refracts light. Here what do I have? I have glass. Okay, so what will happen to this ray? Some of it will refract and some of it will reflect. Okay, this one, the one that will refract, the first image is formed due to the reflection at this surface. The image is dim as very little light is reflected. You remember before we said that when we have incident ray from material to other material, what happens? Some of the ray will refract and the other will reflect. The refracted ray is strong, the reflected ray is weak. So the reflected ray will form the first image, this one, I1. This image will be dim, not clear, because we said this light is what? Weak. Weak ray of light. The refracted light is reflected at the back surface, which is silvered. Now here, what will happen? Only it will reflect. Okay, this refracted ray will reflect. Okay, so this image, the clear image, will be formed by what? This reflected ray. Okay, because this one is reflected by the silvered surface. Other images will be formed by the multiple reflections at the front and the back surfaces. Here what we have all the time, we have total internal reflection, okay? Some of the light will reflect, some of the light will refract, and that's what will happen. That's why you will see in thick glass mirrors, we will see what? That the image is blurry, not clear, because some of the images are formed by refracted rays and the other are formed by reflected or weak reflected rays. Okay? Good. I hope that it's clear. Now, we have something we call it totally reflecting prisms. Do you remember prisms? We talked about them before. We said a prism, it's made of glass. If light, a visible light or white light enters a prism, what happens to it? You can see all the colors that made of this light, white light, okay? All the colors, because each color has a refractive index not the same as the other colors. So what will happen here exactly? Let's see in this case what do we have? Here we have another type of prism. These types of prisms, they have two sides that are perpendicular to each other. So these types of prisms, they have one of the angles is 90, the other two angles are 45. Okay? What happens here? When a light ray enters the prism perpendicularly from one of the sides, okay? What happens in this case? The light will continue moving, nothing will happen, it will not refract. We said that before. If the ray enters with a 90-degree angle, it will continue moving in a straight line without refraction. But when it touches the other surface, this one, here the surface is not a 90-degree, okay? It's not straight. So what will happen? It will reflect. It will reflect. Why? Why total internal reflection we have here? Hello, you know that critical angle for a glass is 42. If angle of incidence for any ray in glass is more than 42, what do we have? We have total internal reflection. Here the angle is 45, okay? Between the incident ray and the normal. What do we have? 45. 45 is more than 42, so what will happen? Total internal reflection also with angle 45. Now what will happen to this ray? It will continue moving in a straight line and it will leave the prism with a straight line, because here what I have, It's perpendicular to the surface. Why do we need these prisms? Okay, these prisms, they change the direction of light by 90 degrees. Sometimes we want to change the direction of light by exactly 90 degrees. I want the light to enter from here and leaves the surface from here. So what I use? I use these types of prisms, okay? Where do we use these prisms? Do you remember periscope? We talked about it before. We said we use in a periscope what? Two plane mirrors parallel to each other. But now, after we took this lesson and we said that multiple images in a thick glass mirror, we have this problem. So it's better to use prisms, okay? To use two prisms so we can see clearly without any problem of blurry images, okay? The same thing happens. Let's see how. A light ray will enter the first prism perpendicular, then total internal reflection, so it will continue moving in a straight line until it touches the surface only, also total internal reflection, because angle of incidence here between the normal and the incident ray is 45, so it will go out to the eye of the observer. Okay, so it's better in a periscope to use totally reflecting prisms better than mirrors. Okay, now we have another use for totally reflecting prisms to do what? To change the direction of light by 180 degree. Here by 90 degree, look, we change the direction of light by 90 degree. In this case, by 180, look, I have the same prism. It's not a new prism, it's the same one. A prism that has two sides that are perpendicular to each other, so 90-degree angle, and the other two angles are 45, 45. But in this case, the light enters from this surface, also with a 90 degree, okay? Also with a 90 degree. Now, when it enters with a 90 degree, it will continue moving until it reach the other surface with, here is the normal, with an angle of 45, okay? 45 is more than 42 critical angle for glass, so the ray will total internal reflection. Here I have total internal reflection, it will move the angle 45, okay? Then here also, here is the normal, the angle of incidence is 45, angle of reflection 45, so it will leave the surface with a 90 degree angle. So here, where do we use this type of prisms? In binoculars. Here, do you know these binoculars? We use these types of prisms in binoculars because you look from this, the light enters from this side. I only change the direction of light by 180 degree. Look, by 180 degree. Okay, so again we have two types of prisms. Not two types, the same type of prisms, but the first one we use it in periscopes because it changes the direction of light by 90 degree. The second one we use it in binoculars because it changes the direction of light by 180 degree. Okay. The last thing in our lesson is light pipes and optical fibers. Light can be trapped by total internal reflection inside a bent glass rod and piped along a curved path. A single, very thin glass fiber behaves in the same way. Look at these examples. These two examples or two objects, they are made of what? A very thin glass fiber. Very thin glass fiber. So the material is glass. Okay? So when light enters, what happens now? It enters with an angle more than the critical angle, more than 42 degree. So what will happen? The light will reflect only. Total internal reflection will happen to the light all the time inside this glass. So the light will not go outside, will stay and trapped inside this glass until it goes out from this side. Okay, and the light enters from here and leaves from here. The same thing here. Look, Here's the normal angle of incidence is more than the critical angle for glass, so total internal reflection until the light leaves from this part. Okay, so now look at fibers applications. Where do we use these fibers? The first thing we use them, doctors, as an endoscope. Doctors, they use these fibers as an endoscope to obtain an image from inside the body. Here's a process, we call it endoscope. For sure you heard about it, all of you. So here's the doctor and here is the light. So what happens in this case? When the light enters, the light will trap inside the glass until it reaches here and the doctor can see clearly what he wants to see. Okay? By engineers to light up some awkward spot for inspection. And the last one, the latest telephone cables are optical, very pure glass fibers carrying information as pulses of laser light. For sure you all saw before these things. What is this? This is fiber. What happens? Light enters from one side. The light is trapped inside this thin glass and it leaves, or we can see the light only from here because it enters total internal reflection all the time, like here, total internal reflection. Then you can see the light leaves this point. Okay? Okay, girls, that's all for our lesson for today. I hope that everything is clear. Study the lesson well, and tomorrow we will start solving paper 2 and paper 4 questions. Okay?